Good morning or good afternoon, everyone. I'm Morgan, and I will be one of your presenters today. I am here based at the headquarters of YellowScan in France. I'm here with Julien, our technical support manager.
Hello.
And we are in direct with Quantum-Systems Martin Herrkammer from Germany. So, first of all, a little heads up with the housekeeping. So as you may know, you're muted for now, but please feel free to write all the questions you want. You have a sidebar on the webinar. Of course, you are able to write any question. We will answer them at the end of the webinar. Your bottom taskbar may have some part of your screen, so please do not hesitate to pass to the use mode, auto hide mode. We will have at some point of the webinar, you will have questions. So we will give you 20 to 30 seconds to answer it. It's really quick. So you will have time, don't worry. And of course, the last but not least, you can watch it again after this webinar. So thank you for joining us today. So a little heads up on the agenda today. Of course, you will have the presentation of the use case, and at the end you get the result of it. You get a little bit of more information about the VTOL drone and of course some LiDAR insights. But now to begin, I will let the mic to our dear friend from Germany, Martin Herrkammer. Thank you, Martin.
Great job, isn't it? It's a large area with limited access. About the measurement of dumps, stockpiles, and excavation volume. What are your options? Measuring with mobile mapping and classical surveying is expensive, time-consuming, and not always satisfactory. The measurement with classic airborne LiDAR is not cheaper and also difficult to plan with regard to the availability of the aircraft. Multicopters are only suitable for relatively small areas up to 160 acres. In addition, it is very risky to operate a LiDAR sensor using a multicopter. The solution is the combination of VTOL fixed-wing UAV and LiDAR. This is very fast, reliable, and the result is a survey-grade 3D point cloud, which is available immediately after landing. Why using a VTOL fixed-wing to carry the LiDAR sensor? A VTOL fixed-wing UAV combines the following features: very high endurance, very easy handling, high flight speed, and vertical takeoff and landing. Now it gets exciting. Let's talk about LiDAR. Julien, please explain some technical details to the audience.
Thank you, Martin. Yeah, we say we made the survey with a LiDAR, but what is a LiDAR? Will you explain briefly for the people who don't know yet what it is? So a LiDAR is a bit like a radar or a sonar, but instead of a radio wave or a sonic wave, we send a light wave, which is also called a laser. So the laser runs from the sensor and it gets reflected on an object here at the top of a tree, and it's sent back to the sensor, and we receive what we call an echo. Fortunately, the laser we can go through the vegetation, and so a part of it will also reach further, another part of the tree, or go up to the ground, down to the ground. sorry, and be sent back to the sensors, and we will get another echo. From that, we will measure the traveling time, and from the traveling time, we can get the distance. With the distance and the orientation, then we can get a position. If you do it once, then you will have 1 point. And if you do it again and again for thousands of times and even millions of times, then at the end, you get a real nice survey. That's a castle in south of France. Okay. If you like the video, show it again. Right. But there is LiDAR and LiDAR, and I would like to explain you now how to measure the quality of a LiDAR system. So there is basically 3 main components about that influence the position of the LiDAR. There is the scanner, there is the inertial motion unit or IMU, and there is a GPS. Each of them have their own error, and this is where the engineering and the design allow the solution to be more or less precise. So if we look at the scanner precision, the scanner will measure a distance. So there will be some error on the distance measured. So the uncertainty on the position will look like this. Then if you look at the IMU quality, the IMU or inertial motion unit records angles, and so the angle precision will be like this, and so the uncertainty will look now like a small box. But if we look now at the GPS precision, because maybe the drone is not exactly here, but it could be just a bit shifted, then it's like if we shift the whole thing. And if we look at the uncertainty box, sorry for my French accent, it's difficult to say uncertainty, then it will look like this, a bigger box. So here are the elements that we use in the LiDAR that was used in the use case in South Africa. It was in the Ultra, we have the VLP32 for the scanner with a precision of 3-4 centimeters. For the IMU, we have the Aplanix APX15, which is a good quality IMU. And for the GPS position, we post-process the trajectory with the post-pack software, with the PPK and infusion, and we can reach the same accuracy than RTK, around 2 to 3 centimeters. A bit more about the scanner now. The scanner, the VLP32, has 32 beams. That's why it is called the VLP32. But there is the irregular beam spacing, which means the beams are closer to each other, close to the nadir. And thanks to that, we can see more details or acquire more details where it matters the most and where there is a less error. The scanner can record up to 2 echo, so there is a strongest and the last return. And it is pretty nice for the drone and the fixed wing. Yeah. Now the LiDAR position quality. If we look at all these elements together, what is the accuracy that we can expect from the Surveyor Ultra? We can reach from all these various elements, and thanks to the design, we can reach an accuracy of 8 centimeters in elevation in Z and 10 centimeters for the X and Y. So now I'm going to show you how it looks like now that you know what is a good quality LiDAR. So let's see now for our products. Okay. Here is the Surveyor Ultra. Here we can recognize the scanner. Here on top we have the flap where you can have the battery or the memory stick with the data. Here we have some connectors, but the system runs independently. So these connectors are just for external power source if needed, but there is internal battery. For an option of the live station, which can have a live streaming, and to record events if you do a flight with a RGB camera at the same time. Here we have the yellow button, and it's actually the only button you need to use on the field to start and stop the recording, and also to turn off. The main aspects of the Surveyor Ultra, the main benefit is, first of all, it's very light. It's only 1.7 kilogram, and that includes the battery and accessories such as GPS antenna. It is very compact, very small, easy to fix on a drone. And we have built-in bore sight angle, which means there is no calibration to do on the field. It's really plug and play, and you even don't need to plug. The Surveyor Ultra can fly up to 160 meters above the ground. So the higher you fly, then the safer you are, and also the wider the swath of acquired field for each flight line. It can record up to 600,000 points per second. So with this high density, that allows you to see more details, but also to have high-speed flights, and still very easy to use. That's our motto. So just one push button. Okay, and now that I've shown you the LiDAR, we'll let Martin to show why it fits perfectly with the VTOL.
Yeah, thank you very much, Julian. The Tron is the perfect platform for the Surveyor Ultra, just introduced by Julien, because the Tron has a maximum takeoff weight of 31 pounds, and it flies with the perfect speed for the YellowScan Ultra at 38 knots. We only need about 10 minutes from the box to the air, and the 90-minute flight time is a great endurance to cover more than 1,729 acres or 2.7 square miles. The drone can carry 4.4 pound payload, and therefore the Ultra fits perfect to our UAV, which can handle up to 23 knots of wind speed. The high quality payload compartments make the drone a perfect platform for the most diverse sensors. The standard payload compartments range from RGB cameras to multispectral sensors to technically perfect integration of the YellowScan Surveyor Ultra. The sophisticated integration prevents vibrations, and there are no cable connections to the UAV. All you need is a yellow button to start and stop the recording before and after the flight. Now let's have a look at the video, showing a bit more about this technology. Here we can see the nose cone with the integrated YellowScan Ultra. It's connected to the aircraft with 4 secure screws, and then the takeoff just by one single button press. The aircraft is doing autonomously a transition, and then it's on automatic flight mode for around about 90 minutes. So we can cover around about 700 hectares of forest, urban areas, rural areas, and the live view station can show you the data in lifetime So you see what you get while the aircraft is capturing the data in the air. Once the mission is finished, the aircraft will return home automatically. It will perform a transition back to the helicopter mode, and it will perform an automatic landing. So there's no much space needed to operate this aircraft. It can lift off and land from any place greater than 5 meters, and it's a very easy operation. So let's summarize the Tron Ultra bundle facts. The speed of the Tron at 38 knots is perfect for the fast YellowScan Surveyor Ultra, and the long endurance allows large survey flights with only one battery for 90 minutes. The point density is with up to 70 points per square meter, good enough for most of the applications, and the Q-based flight planning software helps the customer to plan complex area and corridor mapping projects. It's an easy to operate system with the focus on safety and reliability. So now I would like to hand over to Morgan. Morgan, are you there?
Yes, so guys, as I told you before, there's the poll now. You will have to answer one small question, and then I give you 30 seconds to do it. So which part of this webinar are you the most interested in? You have the choice between the VTOL, the LiDAR, and the use case results. We would like to know what you think about the use case results are coming next. In the meantime, now we're going to talk about the result. The idea is to show you the project characteristic, then the result on the battery use and all these details, and then Julien will show you some cloud station and result live. So now I give the hand to Martin. Thank you.
Thank you, Morgan. Welcome back to South Africa and our coal mine surveying project, northeast of Johannesburg. We had to survey a 1.5 square mile area with only one flight at around about 90 meters above ground. The mission was therefore planned at 60 meters above the takeoff location. And now let's have a closer look at the flight planning with Cubase. This is the Cubase interface, and once we loaded the area, Cubase is automatically calculating the runs, and we can set up the gap distance between the runs, we can set up the altitude, and we could adjust the direction. With a one button press, the software is calculating all the turns, all the flight times, and we can easily add a takeoff and landing location. This is the takeoff location with the transition cone, and with another click we can add landing location with the retransition. And once this is done, we can have a look at the mission information. This is a flight with 53 minutes, pretty close to what we did. This is a bit depending on the wind speed. Today we have an automatic wind detection for South Africa for our northeastern direction with 1.5 meters per second only. In the project, we've been flying with more than 8 meters wind per second. And with another single button press, we are transferring the flight plan to the aircraft. And then we can take off automatically. We fly the mission and we land it. Here's the Tron ready for takeoff. And after the 56-minute autonomous flight, the Tron was landing safely exactly at the takeoff location. So this screen shows the ground station display just before landing. As you can see here in the top, the wind speed is around about 8 meters per second or 60 knots, and the elapsed mission time is 56 minutes, and still there is a remaining battery power of 43%. So let's check the final results. The flight time, as I said, around about 56 minutes. The battery use, 57%, and 240 million points have been captured on this mission. Julian, would you like now to show the final results? I'm pleased to hand over to France.
Yes, for sure, Martin. So for the final results, I will sorry. For the final results, here it is. So we have here the point cloud that has been colorized because there was a flight. But if we look at all the point cloud that's been taken by LiDAR, it was the square that we can see that is larger. So here I want to insist on the fact that this is not a raster, because from far we can be confused. So no, this is really each point cloud, each point of the point cloud has a color. And okay, so if we look at all the characteristics, I can show the classification on the points. So here, okay, it's a mine, open mine, so it's mainly ground, but we can still see a few buildings that are in green and a few vehicles that are in red. Okay, if we look at the building colorized and classification, we can see it's really matched together. So the camera and the point cloud really to match. On the right of the prospect, we can see a high voltage power line, and I will zoom a bit on it, for we can see the power tower, electric tower. Yeah, thin slice. And if we zoom, yeah, zoom, 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 zoom. Yeah, to see the kind of details you can see with the one flight of the Surveyor, the Ultra. So we can see really the structure of the tower. You've seen the power lines before. Okay, let's come back to the global view. And now I can show to colorize the point cloud by elevation. So takes a while. Now can turn. We put the EDL filter to see a bit more to emphasize the relief. And okay, now we zoom and focus on the stockpile and the pits. So you see, if you have some volume calculation, it's very easy with the point cloud. You just delimit the area you need, and you can make all your stockpile calculation and evolution. Okay. Just some zoom on some small details. We have here a dozer, and that we can see very well with the RGB camera, but we can see it also very well on the point clouds. Here we have some warehouses, and we can see the shape of the roof. So now it's time for Q&A. So please don't hesitate to write some questions, and we'll answer them. Morgan?
Yes, so here is going to be my first question. So this might come for Martin. There appear to be seam gaps in between flight lines where data sense density is lower. Is this outcome available during flight acquisition in real time in order to adjust, tighten line spacing during missions, or would it be only noticeable once it's post-production? Okay, so it appears to seem gaps in between flights.
Okay, so you said for Martin, but actually it's for me.
Well, I think it's for you, in fact.
I think actually it's for me.
You know what? Let's share it.
Okay, let's see the presentation. It's sorry.
Okay, while you do this, what software do you use for point clouds colorization?
I used TerraSolid, and where you can you have some module to create auto photos or to colorize the point cloud. So if I go, sorry, tick. So yeah, so for the first question, I will answer in a few minutes. I need to load some data and to show that there is no gap between the flight lines.
Okay, so now I'm going to ask a question for Martin. What is the point cloud accuracy that you can reach with your system? Do you need ground control points to reach it?
You're muted.
No, you go for it. Oh, Martin, you're muted if you try to speak. Life is tough.
So now I can speak. Now I'm not muted anymore. Thank you very much, Morgan. I got the questions. So the overall point cloud accuracy is the result, as Julian tried to explain, of more than one component. It's definitely not correlated with the flight on its own. Well, a little bit by the flight altitude, but mainly it's the result of the IMU, the GPS, and the laser accuracy. And what we see is an overall absolute accuracy, which is just better than 10 centimeters, so something around 5 and 10 centimeters. But the relative accuracy is much higher. So I would say the relative accuracy of the point cloud is more closer to 4 centimeter or 5 centimeter than it is to 10 centimeter. For sure, the density is something we can influence by our aircraft. We can fly lower to get a higher density and higher to get a lower density. And if you would please share my screen, Morgan, I can show you what role the altitude plays on data capturing with the YellowScan Ultra.
Yeah, you have now the screen.
I have now a screen, yeah. So while we've been talking, I opened Cloud Compare, and I'd like to show you 3 missions. From this year, we captured data from 3 different altitudes. As you can see here, there's one flight at 160 meters above ground. So this is a couple of runs in 160 meters above ground. And as you can see, there are no dropouts in the area. The end is the agricultural fields, which are without vegetation for this moment. It's just in spring. Before we can see the wheat coming out of the ground, we can see single trees standing here on the field, and we can see the forest, and we can see a lot of ground points in the forest, even from 160 meters. However, when we fly lower, I will now activate the 120 meters, we get more details. I deactivate the 160, so now you can see we get more details on the single trees, on the standalone trees, and we get much more details on forest areas, because there are just more points hitting the ground, and there are more points hitting first and last pulses on different places in the forest. So in the lower vegetation, in the middle vegetation, and the high vegetation, while in the 160 meter flight, we pretty much only hit the high vegetation. And now I will show you another data set from 60 meters above ground, and you will see some cables, some kind of power lines, but these are telephone wires which are only 3 meters above ground. This is a very small telephone wire with wooden poles, and we can see that we clearly got all the 3 wires from 60 meters above ground. That means we are still more than 55 meters above the small and thin wires. And we got a very highly accurate and dense point cloud on the forest. and on the single solitaire trees. So again, if we watch this tree here at 60 meters, I just let it activate, and maybe I give him a little eye dome lightning so we can see it a little bit clearer. Now I deactivate the 120 meters. This is 60 meters. This is 120 meters. And now I will activate the 160 meters. This is 160, and this tree seems to disappear because there are not enough points hitting the tree at 20 meters per second. But if we zoom out, we can see that we still got a nice terrain model from 160 meters above ground. I hope this answers the questions. And as you can see here in this data set, there's definitely no gaps in between the runs. Gaps are mainly caused by too great distance between the flight lines. The rule is the distance between the flight lines we use is 1.5 factor of the altitude. So if you fly at a 100 meter altitude, the spacing is 150 meter. If we fly at 60 meters, the spacing is 90 meters. That's the rough rule, which I came along with, and it's working since now. It's working for every single project. And Cubase is very handy to assist. And there are new features in Cubase for corridor mapping where you can fly along road structures, power lines, and so on. And Cubase is taking over all your basic calculations for the overlapping and for the point density. And so it's an easy to use system bundled together with the Tron. And now I give it back to the microphone. I give it back to Morgan. Morgan, are you there?
Yeah, I'm there, but I think Julien wanted to add something to your answer, so I will let him go.
It's just in the question there were also do you need GCPs? And no, that's one of the main advantage of LiDAR compared to photogrammetry. It's you don't need ground control points to reach this accuracy. I would like to come back to the previous question. If I can have the screen. The one about the gaps between the flight lines. So this is the data set that we were showing before. Just to show you I'm not lying. If I show here the points per flight line, there are one color per flight line, and no, there is no gap. Maybe it was because of the refreshing time of cloud compared to display all the points. I remind you there is more than 240 million points. But no, there is absolutely no gap here. Okay, can go to the next question.
Okay, thank you. So we're going to do 3 more questions and we will go on. So next question is for you, Martin. Can you tell us how the Tron take off and land that you just showed us? And then what is the capacity of wind that it can support? And as well, can live station be included in this solution? Martin, are you there? You might be muted.
Yeah, so now I'm online. Yeah, I got your question. So the takeoff and landing of the Tron, as you might have seen in the video, the Tron has 4 engines, 4 motors, and they can be aligned. They can be aligned to the front, so as a standard aircraft, or they can be inclined to the top, so that there are rotors like a helicopter. So in the rotor configuration, the aircraft is lifting up onto a certain level, like 30 meters, which is a safe altitude, and then the Tron is performing an automatic transition, moving forward and switching to aircraft mode. So this is something which is automatically done by the system and not controlled by the pilot. So it's completely autonomous. So in fact, what you do is you have a remote control, you press one button, which is called takeoff. Then the unit is taking off and automatically doing a transition for the forward flight. It's doing the mission. The pilot could interact at any time and get it back to the landing place or to fly manual maneuvers to avoid air traffic. We can for sure also show other air traffic with a transponder signal on our ground station, so we can avoid air traffic if necessary, and then resume the mission. Or the aircraft just follows its mission, comes back to the landing place, it's slowing down, it's doing a transition to helicopter mode, and descending slowly until it is around about 5 meters above ground, and then the pilot is using the left stick very slowly to the bottom side, and it's descending, and once it's touching the ground, the motors are automatically switched off. That's quite easy. So Morgan, what was the second question?
The second question is that can we use the live station with this combination?
Yes, we have the opportunity to use the live station. It's just a matter of data transfer. What we now would use is a 2.4 gigahertz modem to transfer live data. And with this modem, we can roughly get a distance of around about 10 kilometers to transfer the live laser data, to have a live feedback on the ground. However, it is not necessary to do, because that's my experience in the field. If you do a nice planning, a good flight planning, you can definitely be sure that the data is fine afterwards. And if you check after landing, what I did in South Africa, so after landing, I plugged off the USB stick from the scanner, I plugged it to my laptop, and immediately I could see what the result is. So there's no big need having a live view for the point cloud. It's just distracting the pilot. In my opinion, the pilot should watch the moving map and the other aircrafts moving by watching the transponder signals, or watching the sky to monitor the aircraft to make sure that there is no collision with obstacles, with other aircrafts, with helicopters and so on. So I better like to spend more time watching my aircraft than watching a live data stream of laser data, because I'm sure the data is fine afterwards. And if not, I have to repeat the flight anyway. Morgan, are you there?
Yeah, hi, I'm there. So we got a lot of questions on GCPs, and I guess Julien can have a share insight with you on this matter.
Yeah, so there is one question, sorry, I can't see who wrote it, asking if we use GCP, even if we don't need it, but if we use GCP, can we increase the accuracy greater than 5 centimeters? Yes, absolutely. You just need some detail that you can see on the point cloud and GCP, and after you can do some matching and move the point cloud globally, or to do some rubber sheet fitting and reach accuracy to 3 centimeters. Another question say no GCP, but did you use a GPS base station and PPK processing on this point cloud? Of course, we post-process the trajectory. It is not PPK. So yes, we had a GPS base station, but in post-pack, it uses the infusion algorithm. So it does the PPK processing. So let's say a comparison of a GPS position, but it's actually using the inertial data logged internally at 200 Hertz as the base for the computation. And it goes to feed the inertial algorithm, the inertial computation with the GPS position. So at the end, we are much more precise than just a PPK, and especially that will compensate and avoid all the heading drift that we often notice on the long flight lines, up to a certain extent, of course.
Okay, thank you. Do you want to add something, Julien, maybe?
No, can go to the next question.
Okay, so the next question is, what is the FOV assuming swath spacing 1.5 altitude?
The field of view. The field of view is actually wider than 1.5 times the altitude. what you can record is 3 times the altitude. So if you fly 100 meters high, you can have a swath of 300 meters. Anyway, we recommend to have a coverage overlap, sorry, of 50%. Once again, this is not mandatory because the LiDAR don't need to have some overlap to fit the lines together. It is absolutely referenced directly, but it's just to give more chance, more opportunity to laser beams to go to see things from different aspects, and especially when you have vegetation, it will let the laser beam go through the leaves and the canopy from different paths, and then you have more chance to reach the ground.
So now a question for you, Martin. The point cloud of the mine in South Africa had real colors. Did you perform a separate flight taking pictures, or the VTOL can together, or the VTOL can take them together in the same time?
Yeah, got that question. The answer is quite easy. What we did, in fact, is we used the Tron with the LiDAR scanner, and at the same time, parallel to this mission, we've been using our smaller aircraft, the Trinity, which is a below 5 kilogram aircraft, much cheaper than the Tron, with a Sony camera, with a 21 megapixel camera. And this flight was performed with PPK. So we've been using post-processed imagery. And the order image we created has the same or even better XY accuracy than the point cloud. So it was then quite easy to overlay the aerial image, the order photo, to the point cloud and to write the color numbers of the order image to the point cloud points. So the RGB colorizing was done afterwards with an order image captured by our Trinity. The reason why we do not put a camera to the Tron is quite easy. LiDAR and cameras are not fitting together that good, especially not at this altitude, because the Tron is flying at a high speed and the LiDAR is looking at a very flat angle to the side. So the field of view of the camera is much smaller, and we would need more than 3 cameras to capture the same area like the laser is seeing. And the cameras we can buy right now, we can purchase right now, they are limited with the intervals. So the best we can get is around about 2 images per second. And this is still not good enough to get enough overlap to calculate a good order image from the same flight path we are using with the laser scanner. So that's why we use 2 different flights, and there are 2 options for the client. One is using the Tron 2 times, 1 time with the LiDAR payload compartment and 1 time with the camera payload compartment. And there we are very flexible with the cameras. We can use cameras with 40 megapixels or cheaper cameras with 20 megapixels. Or the customer uses the Trinity and the Tron. And this is maybe a more flexible investment, because then the Trinity can also be used for other smaller projects where it's just about auto imaging and raster DEMs where we don't need the LiDAR. So my recommendation is investing in a Tron with a LiDAR, and secondly in a Trinity with a RGB camera to get colorized point clouds.
Thank you, Martin. We have so many interesting questions, so we will go on with 2 or 3 more, and then we will wrap up this webinar. The next one is for Julien. Is the file recorded at ultra open LiDAR format? Software for processing the LiDAR data from ultra, or the Tron ultra, and software to be purchased in bundle?
Okay, I will answer to the first part of this question. So first of all, the LiDAR, we can generate it in a LAS format or in a TXT. That's After, if you need another format, then you will need to convert it. Software for processing the LiDAR data. Okay, what we get from the Ultra, we have 3 different files. I can even, the best is to show you these 3 files. Anyway, so we have this cloud station, and when we open, yeah, actually there is a filter. Yeah, we have a filter. We have the APX file, and that is where the GPS position. We have the T04 file, which is the raw data of the IMU, and we have the PUC file, which is a scanner file. And in the cloud station, we will do the merging of the 2 solution, so the position and the scanner. It's loading up. Okay, we can here put the PPK solution to refine the trajectory. So that's how it was done. And this is where we select the flight lines. After, you just need to press play here, and you will generate the last files. Are the Tron Ultra and software to be purchased in bundle? Concerning at least the post-processing, the LiDAR, the Surveyor Ultra comes with the post-pack software. It's part of the price. So the trajectory post-processing is included. For Cubase and so on, I will let Martin answer. Martin?
So, Munich.
Yes, Munich is there. Morgan, which question is still open?
The question is, are the Tron, Ultra, and software to be purchased in bundle? So we talked about the Ultra and the software processing. And can you talk about the Cubase? Is it included in the price? Is it?
Yes, we didn't yet talk about price. So we sell all our aircraft in complete bundle packages. So everything is out of the box. It's a turnkey solution. So what a customer gets is the transportation case with the aircraft, with the flight planning software, with the ground control software, with flight batteries, remote control, and every option the customer needs, inclusive batteries, to operate the system. Which is not what is not included, that's the payload. So for example, the Tron is 45,000 euro, and then we have different payloads, and the LiDAR payload, for example, is 130,000 euros. And so from there, it's up to the customer to decide whether to buy 1 payload or 2 payloads or more batteries. And of course, we also offer some spare parts like separate wings, elevators, rear fuselage, front fuselage, nose cones, etc. So yes, to answer the question again, everything the customer needs and everything we have been showing is included. And we would be happy to show all this in detail on the Intergeo if some of the guys watching today would like to visit us at our booth.
Perfect. Thank you, Martin. Perfect. So I just want to answer 2 questions. I know that some people have missed the beginning of the webinar. Yes, the webinar was recorded, so you will have it just following, just when it's finished. And you can receive as well sending an email to me or to contact, and you will receive the presentation. So now the last question is going to be for Julien, then we wrap up this webinar. We have a question on, can we use a LiDAR over the water?
Okay, to go through water, you depend on the bandwidth that you use, the frequency of the laser that is used. We use a near infrared, so unfortunately it will be absorbed by the water. You get very, very few reflection over water, so maybe close to the nadir. And otherwise, now it's all reflected, and it's really not ideal. But on the drone world, the scanner, the LiDAR that can do bathymetry, so green, I think there's very few and they're all very heavy. So, but basically no, it's really not designed for that.
Okay, thank you, Julien. So we received more questions. We will, of course, answer them after the webinar directly to your emails. So thank you for your this interaction with us. So now I will show you a little bit more application on what Quantum and YellowScan can do together. So this combination can as well be really good for forestry projects, as well as corridor mapping. So if you want to have more information regarding this, do not hesitate. And this is a variety of applications thinkable. So you will have the opportunity to read everything. So when you will receive the presentation. 3 key points to remember to this presentation. First of all, thank you for coming. And we want to emphasize that it's easy to use, it's efficient, and of course, reliable. So please do not hesitate to ask any questions, and we'll be happy to answer you guys. And so to answer your questions, you will be able to meet us at IntGeo. So Quantum System will both be in all 12. So you can see here the booth. We have also a quantum demo every first Tuesday of the month, so do not hesitate to go on their website, www.quantumsystems.com. And of course, in March, we're pleased to organize our 3rd user conference, LiDAR for Drone, in March in the south of France. And you get a discount code, and we'll be happy to meet you there and to share with you use cases, demos, and of course a networking session where you can enjoy French wine and some cookies, and maybe a cake cupcakes if there's more American than European. Well, thank you guys, and we'll be happy to see you soon. Okay. Bye bye. Thank you.
Bye.
Bye, Martin.
Bye bye, Munich.
Bye, Munich.
Yeah, bye bye from Germany too. Have a good day in France and all over the world, and especially a good day for our friends in the US.
Yes. Goodbye.
Bye.